Hi, thanks for attending this talk. The title of this talk is Capacity Optimality of AMP in Code Systems. I'm Lei Liu. This is a joint work with Chu Longyang, Junjie Ma, and Li Ping. The full version of this work is accepted by IEEE Transaction on Information Theory and is also available on arXiv. This is the content. First, I will introduce the uncoded large random magical system and the AMP algorithm. Then I will introduce the capacity of large random magical system. After that, I will show you the capacity optimality of AMP in coded large random magical system. I will also show you some simulation results and finish this talk with conclusions. In this work, we consider a very simple linear system, y equals to ax plus n. N is a noise vector, and A is a IID Gaussian matrix with a very large system size, n, m goes to infinity. And the element in X are IID with distribution Px. If X is Gaussian, then the optimal solution is a well-known linear MMSE. However, for other discrete distributions, for example, QPSK and Brody Gaussian, the optimal solution of this problem is generally a bit hard. And the AMP is the state-of-art algorithm to solve this problem. This figure gives the block diagram of the transmit. And this is the modulation constraint of X. This is the linear interference constraint of X. And the AMP receiver solves the problem by these two local processors. And this is the nonlinear detection demodulation for the demodulation constraint of X. And this is a linear detection for the linear interference constraint of X. And then we do the iteration between these processors. The expression of a linear detector is given by this formula, and the expression of a nonlinear detector is given by this formula. The key point of AMP is that it uses on socket plane to solve the correlation problem in the iterative process. Why we consider AMP? AMP has many advantages. First, it is low complexity since it uses a very low complexity multi-filter detection. And the second, it is MMSE optimal under a Unicode fixed point. It is robust and works for arbitrary input distribution of X. And it is also very easy to analyze. It is proof that the state evolution of AMP is correct. This is a block diagram of the state evolution of AMP, and this is a transfer function of the nonlinear detection. And this is a transfer function of the linear detection. They are given by these two formulas. Then we go to the capacity of the large random matrix system. For Gaussian singular ring X, if matrix A is unknown at transmit, then the capacity is a well-known minimal Gaussian capacity given by this formula. And this capacity can be achieved by the famous tuple linear MMSE receiver in these two references. And for non-Gaussian X, and if matrix A is known at transmit, then the capacity can be obtained by singular value decomposition with Markov water-filling in this reference. However, for non-Gaussian singular ring X, if A is unknown at transmit, then the capacity problem is not trivial. So the motivation of this work is like for non-Gaussian X, for example, QPSK, if matrix A is unknown at transmit, then what is the capacity and how to achieve this capacity? Recently, the capacity problem has been solved in these two references. And as we can see, this theorem gives a capacity of the large random matrix system. And I don't go to the details of the capacity since it's too complicated. Next, I will show you very simple graphical interpretation of the capacity. Before I introduce the graphical interpretation of the large random metric system capacity, I would like to show you the area property of cis or AWGN channel. So the capacity of the cis or AWGN channel is given by the mutual information MMC lemma. It shows like the capacity of cis or AWGN channel is given by the area covered by this blue line. The blue line is the MMC function of the cis or AWGN channel. North star is the SNR of the cis or AWGN channel. For the Gaussian case, the MMC function is given by this 1 over 1 plus law. And then we get the famous Xianglong theory. So the question is, what is the area property of large random metric system? Then we correlate this is a transfer function of the AMP, and this is a transfer function of nonlinear detection, and this is a transfer function of linear detection. And this is the blue line denotes the transfer function of nonlinear detection. The red line denotes the transfer function of linear detection. And we prove that the capacity of large random metric system equals to the area covered by the blue line and the red line. The area can be calculated by this formula. And therefore, we also give an alternative proof of the large random metric system capacity based on some properties of AMP. Now we already know the capacity of the system. However, how to achieve this capacity is still unknown. So our question is, can AMP achieve the capacity with coding? Then I will show you the capacity optimality of AMP in coded large random metric system. That is, AMP can achieve the capacity if we properly design the coding. These slides I will compare the uncoded system and the coded system. As we know, uncoded system cannot achieve error-free performance. Therefore, we consider coded system. For the coded system, there is an additional code constraint here compared with the uncoded case, and the other conditions are the same as the uncoded system. And at the receiver side, there is an APP decoding corresponding to the code constraint at the transmit side. So this is the state evolution assumption for this work. As we know, for uncoded IDX, the state evolution of AMP was proved in this reference. However, for the coded X, the state evolution of AMP is still not rigorously proved. Therefore, in this work, we assume that for the coded X, the state evolution of AMP holds. We assume that the performance of AMP can be checked by these two formulas. The difference is that we consider a code constant and the MMC function in the nonlinear detection. Then the question is how to find the optimal coding for AMP. This is a graphic illustration for uncoded AMP. As we can see, for the uncoded case, the AMP always converges to a non-zero error performance. Therefore, we cannot achieve an error-free performance. However, for the coded case, we can get a better coding transfer functions because we consider coding here. Therefore, if the transfer function of the decoding lies below the red line, then the AMP can converge to error-free performance. Then I will show you some properties and the conditions of the coded AMP. The first is the coding gain. Since we consider coding, the transfer function of decoding is upbounded by the blue line, is better than the blue line, the uncoded line. Second is the error-free condition. So if we need an error-free performance, then the transfer function of the decoding should lies below the red line. Therefore, the green line is also upbounded by the red line. Lastly is the error property. The area covered by the transfer function of decoding equals to the achievable rate of AMP. Therefore, to maximize the achievable rate of AMP, the optimal choice is that we design a code to ensure that the transfer function of decoding matches with the blue line before this fixed point and match with the red line after this fixed point. Therefore, the achievable rate of AMP equals to the area covered by the blue line and the red line. And as I mentioned, the area covered by the blue line and the red line is the capacity of the system. Therefore, we have this theory. AMP achieves the constant capacity of large random matrix system. And there are two conditions for this optimality. The first is we assume that there is a unique fixed point of these two lines. And we assume that there exists such code whose transfer function can match with the blue line and the red line. And for the Gaussian singularity, we can prove that these two conditions strictly hold. Then is the simulation result. These two figures give the achievable rate comparison between AMP and the tubular MMCE. This is the Gaussian capacity, and the red line is the achievable rate of AMP, and the blue line is the achievable rate of tubular MMCE. As you can see, for the different system load and for the different input distribution, QPSK, 8 PSK, or 16 quant, the AMP can get a significant achievable rate improvement comparing with the tubular MMCE. These two figures give the BR comparison between AMP and the tubular MMCE with optimized irregular ARDPC code. As you can see, this figure gives a curve matching of the AMP with irregular RDPC code. And this figure gives a BR performance comparison of AMP with optimized irregular RDPC code and the tubular MMCE with optimized irregular RDPC code. And as we can see, AMP has significant improvement in SNR. There is about 3 dB gain in SNR comparing with the tubular MMCE. This figure gives the BR performance comparison of AMP with optimized irregular RDPC code and unoptimized RDPC code. And the blue line is the BR performance of AMP with optimized irregular RDPC code. And the red line is the AMP with the standard seesaw irregular RDPC code. And the purple line is the AMP with regular RDPC code. For the different system load, and the AMP with optimized RDPC code can always have significant performance improvement than the standard irregular RDPC code and the regular RDPC code. Then is the conclusion. In this work, we provide a graphical interpretation of the large random matrix system capacity given the input distribution Px. And we prove the capacity optimality of AMP for arbitrary input distribution and match the FEC coding. And we assume that there is one fixed point of the coded AMP and the state evolution of coded AMP is correct. And we also show that AMP outperforms the state-of-art tubular MMCE in achievable rate and in the BR performance. And we show that the code optimization for AMP has significant performance improvement. Okay, that's all. Thank you. Thank you for your participation. So if you have any question, you're welcome to contact with me by this email.